Now we want to talk about the second kind of organization, the fully associative organization. But before we do that, I think one of the things that I said in the previous video might have given a misimpression. I said that cache blocks can be of varying size. In fact, that's true over different systems. Some systems have blocks that are different sizes than others. But in a particular system, usually all cache blocks and all cache lines are the same size. I say usually because some systems have lines that are multiples of other lines in size, but let's not get into those complexities. Just consider that in any system we're going to be talking about, all the cache blocks and therefore all the cache lines are the same size. Now remember that in a direct mapped cache, a particular block, when brought into the cache, can be placed in only one line. The fully associative organization is the opposite of that, where any block that's brought into the cache can be placed in any line. So that means that when we bring a block in our example cache, we have a choice of 128 places where to put it. And if you look at the organization as we show it here in the diagram, you can see that line 0, that block 0 over here from main memory can go into line 0, it can go into line 1, it can go into line 127, or anywhere in between. In ditto for block 1, that can go anywhere. So any block from main memory can go anywhere in the cache. Because of the fact that any block can go anywhere, we don't need a field telling us which cache line a particular block needs to go into, and therefore we don't have any index field at all. We do have an offset field, of course, because that tells where in a particular block a specific word or byte is located. But the rest of the address consists entirely of the tag field. Therefore, our tag field is 14 bits wide. And of course, each line has its own tag associated with it. When the line is in use, the tag contains the high order 14 bits of the main memory address of that block. So to search for a word in the cache, we have to compare the leading 14 bits of the address with the tag of all lines, and we need to do it simultaneously. So now, instead of having a single 7-bit comparison going on, we have 128 14-bit comparisons, and that obviously makes it a lot more complicated to build this cache. But after we determine whether the block is in the cache, then we simply select the desired word from the line and then read it out, and then we've got the word that we need. Our processor has the word that it needs. The advantages of this organization are that we have minimal contention for lines, because we can always put a particular block that's brought in any line, and a wide variety of replacement algorithms. Many of you have probably heard of LRU, or least recently used. There's an easy hardware way to implement that, and so that's pretty commonly used, at least for caches that aren't too very much associative, but for caches that are fully associative, least recently used is going to require too many bits of state, so you're not going to do that. But instead you would probably have some approximation of least recently used, which might be the least recently used block and the least recently used group of lines or something like that. So a wide variety of replacement algorithms are feasible. That's the point I wanted to make. On the other hand, though there are a lot of strengths of this organization, it is the most expensive of all organizations, and for caches of any reasonable size, fully associative is completely beyond the budget of the processor, both in terms of the amount of logic you'd need and in terms of the amount of space it would occupy on the chip. Besides, it's not even that fast, because you have a lot of levels of logic that comparisons need to transit before you can find out if there was a match anywhere. And so the lookup also tends to be slow. So even though you have fewer misses, a hit takes you longer, and that means that a fully associative cache isn't as advantageous as it would look at first glance. Well, now that we've talked about these two organizations, we can talk about how caches operate in general. The process of searching a fully associative cache looks a lot like searching a direct mapped cache. There are only a couple of small differences. In the beginning, you start out with a virtual address, and then with the virtual address, you need to divide it into two parts: the page number and the byte within the page. Well, if you studied operating systems, you know that most likely the page number is going to be looked up in a translation look-aside buffer, or TLB, because we want to be able to translate virtual addresses to physical addresses quickly. Therefore, you search the TLB, and if there's a hit, then from that you just get out the leading bits of the physical address, and you can go concatenate it with the offset with the byte within page. Of course, if there is a replacement that takes place at that point, then you need to do something more complicated. But even if there is no replacement, note that I've got this little block here that says update replacement status of TLB entries. If you use anything like least recently used replacement, then if you just reference the line that was least recently used, obviously it's no longer the least recently used line, but it becomes the most recently used line. So you need to update the bits that record which line is least recently used. And that's also true if you have some kind of approximation to a least recently used algorithm. So given that, we read out the beginning of the physical address, or the block number, which is the most significant bits of the physical address. And then we can concatenate it with the bytes within the page, and then we get this physical address. Well, okay, but let's assume, before we go on to talk about the physical side here, let's assume that there was no TLB hit. If that's the case, we need to get rid of some TLB entry so we can replace it. We need to select a TLB victim. And at the same time we're doing that, we're translating the virtual address to the physical address. And once we translate the virtual address to the physical address and decide where it's going to be put, that is which the victim is, we can enter the new virtual and physical address pair into the TLB. So now the TLB can translate that and says, if you go to this virtual address, you're getting this virtual page, and I know where that is. Okay? So that's the virtual side. But the physical side here starts with taking this physical address, which consists of a block number and byte within block. So let's talk about the block number first. We need to determine whether that block is held in the cache. And so, if it's a fully associative cache, we have to search in lots of tags to see if any match. And if there is indeed a cache hit, then we can fetch the block from the cache, select the desired byte from the block, and send the bytes to the processor, and we're all done. But if there was no cache hit, it becomes a little bit more complicated, because then we need to select some cache line to replace so we can bring in our new data. That's called selecting a victim. At the same time we're deciding where we're going to put the data, we're also beginning to fetch it from main memory. And once it returns from main memory, then we can store it in the desired place in the cache. So that's how this all works. That's how address translation works. And we've talked a little bit about fully associative, or about the fully associative organization and some of its strengths and weaknesses. In our next video, we're going to be talking about set associative caches.